Indistinguishability by Adaptive Procedures with Advice and Lower Bounds on Hardness Amplification Proofs. This is a work by Aryeh Greenberg, Ronen Chartier, and Emanuele Viola, and Ronen will give the talk.
Okay, so good afternoon, and thank you for staying this long. Cheer up, right? I mean, only 3 more talks to go, right? Okay, so I'll be talking about hardness amplification theorems. So these are theorems which transform mildly hard functions into very hard functions. So specifically, what are these? So the theorem has the following form, right? You give me a Boolean function with a property that for every circuit C in some circuit class, think P/poly, the probability that the circuit computes the function correctly on a random input is smaller than 1 minus delta, and think of delta as small, say 1 over 10, or sometimes even smaller, right? And I'll call a function like this a 1 minus delta hard function, okay? So the theorem says something like that. If you give me a function like that, I pass it through my amplification technique, okay? And I obtain a new function, f prime, where this function is harder. In what sense is it harder? It's a half plus epsilon hard function. Namely, the probability that the circuit computes a function correctly on a random input is at most half plus epsilon. And think of epsilon as small, say 1 over n, or sometimes negligible, okay? And as you all know, we really like very hard functions, functions with a success probability half plus epsilon, because we use them all over in crypto, in de-randomization, and in complexity theory. And essentially, what usually happens is that hardness amplification results allow us to relax assumptions. Rather than assuming that we have very hard functions, we can assume that we have mildly hard functions, okay? So let me give you an example. This is probably the most famous hardness amplification theorem out there. This is Yau's XO lemma, and Yau's XO lemma says the following thing. So you give me a function f, and I amplify it. I construct this new function f prime. What is f prime? F prime is the function that receives t inputs for f, applies f individually on each one of the inputs, and then XOR the outputs. So that's a function f prime. That's the amplification construction. And the theorem says that if you take sufficiently many inputs, if you take log n inputs, then the following hold. If your initial function was, say, 1 minus 1 over 10 hard for P/poly, then the new function, the target function f prime, will be half plus 1 over n hard for P/poly. And this is great, right? I mean, we all like this theorem. It's been there, right? I mean, since the late 80s, and it's wonderful. But you can ask, what about lower circuit classes? Okay? So what do I mean by lower circuit classes? Here is a map of the lower complexity classes realm. So on the left-hand side, I have AC0, the class of constant depth circuits with unbounded fan-in, and the standard gates, and or and not. Then, next to it, I have AC0 with parity gates. These are constant depth circuits where I also allow parity gates. Then TC0, where I also throw in majority gates, and then stronger classes, NC, P/poly, and whatnot. Okay? And there's a dividing line between these classes by the majority function. So what do I mean by that? Classes on the right-hand side of this dividing line can compute majority by definition, whereas we know that the classes on the left-hand side of this barrier cannot compute majority. We have lower bound against these classes. So we can now ask ourselves, which one of these classes in the complexity realm can we substitute for P/poly in this theorem, right? So that's the question I want to ask. And it turns out that for each one of the classes on the right-hand side of the barrier, the stronger classes, we can do hardness amplification. We can replace P/poly by any one of these classes, and the theorem remains true. But unfortunately, right, for each one of these classes, natural proofs of Razborov and Rudy kicks in, and we don't know how to prove lower bounds, right? On the other hand, if you go to the other side of the barrier for weaker classes like AC0 or AC0 with parity gates, we have lower bounds, right? And that's great. Unfortunately, we don't have any hardness amplification result for any of these classes. And 10 years ago, in a paper with Viola, we termed this the lose-lose principle, right? So this is like no free lunch, right? You can only amplify the hardness, but you don't have. Okay? That's life. So, and this is especially frustrating for the case of AC0 with parity gates, because for AC0 with parity gates, we have unconditional lower bounds, mildly hard functions, but we don't have a very hard function. We don't have a half plus 1 over n hard functions for AC0 with parity gates. This has been open for like 25 or 30 years now. And this is the main barrier. This is the main barrier in constructing pseudo-random generators for AC0 with parity gates, because in order to go through the hybrid argument, we need to get functions that are very, very hard. Okay? So it would be very nice if we could prove exolemmas for a constant depth classes. So what is this paper about? So there's previous work by the paper I told you about with Viola and another paper of Gutfreund and Rothblum showing that this barrier, the fact that we cannot do hardness amplification for low classes, cannot be bypassed by certain black box techniques. And the emphasis here is on certain, right? Previous work was able to rule out some black box techniques. And what we do in this work is that we rule out general black box techniques. So what now we have like a really, right, like before that we had like a weak excuse, and now we have like a really strong excuse why we don't know how to prove hardness amplification results for constant depth circuits. Okay? So that's the first result I want to talk about. A second problem that you have in hardness amplification is unrelated to circuit depth. So forget circuit depth and now think about size, circuit size. Okay? So here is a quantitative version of Yao's XO lemma, and it says the following. For any epsilon and delta, if you take sufficiently many copies, if t is some function of epsilon and delta, then you have hardness amplification. Specifically, for every function f, if f is 1 minus delta hard for circuits of size s, then the target function f prime will be half plus epsilon hard for circuits of smaller size. For circuits of size s prime, where s prime is s over q, and in the best proofs that we know, q is something like log 1 over delta over epsilon squared. Okay? So this is great, we like it, but there's a problem, right? The circuit that is asked to compute f prime is smaller than the circuit that is asked to compute f. Well, that's unavoidable because we proved by reduction. But the point is that it's not only smaller, it's much smaller. It's q times smaller. And this is a problem because in particular it means that if you give me a function, and no matter how many repetitions I take, no matter how many copies I take, I can never get epsilon below 1 over s or even 1 over square root of s, right? So this is really disappointing. And by the way, the sentence over there was structured to look like a Trump tweet. So if you guessed that, then that's great. So what do we do in this work? So in this work, we show that a loss of this magnitude, a loss of q of log 1 over delta over epsilon squared, is indeed necessary for general black box techniques showing hardness amplification. And again, this improves upon previous work, the paper I told you about with Viola and another paper with Artmenko, in which we had partial results and we couldn't quite get the right thing. Okay? I should also say that this also applies for the case where we start from worst case hardness, which is also widely considered. So this is capture when delta is 2 to the minus n. And in fact, this case and similar cases are closely related to locally decodable, least decodable codes. Okay? by the work of Sudan, Trevisan, and Vadan. So if you are a coding theorist, then what we really show is we show a lower bounds on the complexity of decoding algorithms for a local decoding of least decodable codes. Okay? So that's another interpretation of our results, but I'm not going to explain why that is. Okay, so, right, I mean, I'm going to tell you about a black box technique, so I need to show you my black box model. So what is black box hardness amplification? What are black box hardness amplification theorems? So they consist of two parts. The first part is a construction map, the amplification map, which you give this map f, and it gives you the function f prime. So that's the construction. The second part is a proof or a reduction. So what is a proof of correctness? It's an oracle procedure, this reduction over there, which has a property that if you feed it with an adversary C, which breaks the target function f prime, then it implements an adversary C, which breaks the original function. And this demonstrates the correctness of a hardness amplification. If the target function is not hard, then the original function is not hard. And when we say black box, what we mean is that this reduction has black box access to the adversary. So here is the reduction, here is the adversary. I wrote the truth table of the adversary. And what we imagine is that the truth table is inside this black box, and the only way that the reduction can interact with the oracle is by making queries and receiving answers, right? So it has random access into this table. So what do I mean when I say general reductions and that previous work couldn't handle general reductions? So here there are two issues. First one is adaptivity. So general reductions are allowed to be adaptive. Namely, when they make their next query, they can make it as a function of what the answers that they received on previous queries, and some of the previous work weren't able to prove lower bounds against adaptive reductions. A second issue, which is more important, is that in this setting, reductions are allowed to be non-uniform and take advice. So what do I mean by that? So it turns out that in this setting, the reduction has the following power. It can call a friend, right, this suspicious-looking fellow in a raincoat, and this suspicious-looking fellow can take a look inside the black box, look at the entire truth table of the oracle, and then transmit a short advice string to the reduction. And then the reduction begins to work. Right? So this sounds very mysterious, but right, I mean, that's the way these reductions work. They all use this kind of suspicious guy in a raincoat, and they have to. We know that they have to. If you're a coding theorist, you're used to that because the ratio between non-uniform reductions and uniform reductions is kind of like the ratio between list decoding and unique decoding. In what sense? You can think of a non-uniform reduction as a list of reductions, one for every possible instantiation of the advice string, right? So that's really the connection. So what we really show lower bounds on the circuit depth of such procedures, of a reduction. That's the first result. And the second result is a lower bound on the number of queries of such procedure. And the new thing here is that we handle general reductions that can take a polynomially long advice string and are adaptive. Okay? So that's what I wanted to say about reductions. And let me jump into a component in the proof that is unrelated to black box issues. So if I've lost you by now, or if you don't care about black box issues, this is the point where I want to regain your attention and show you something else that, right, I mean, it's not complicated. It's a very simple thing, but it might be useful in other settings. So, new problem, okay? So this is the setup for this new problem. We have n random bits, R1 up to Rn, which are unknown to an adversary. But somehow, the adversary gets to use this suspicious fellow, right? And this suspicious fellow tells him A bits of advice about the random string. So this means that now, from the point of view of the adversary, the distribution of a random string has changed. It's no longer distributed like R. It's distributed like a random variable X, which is R conditioned on A, where A is a large event. A is an event that occurs with probability 2 to the larger than 2 to the minus A if A is the number of advice bits. Another way that you can think about it is that initially the random string had full entropy, entropy n, and now after A bits of advice were given about this random string, now from the point of view of the adversary, the random string looks like a distribution X, which is missing A bits of entropy. So the entropy of X is larger than n minus A. This is the only thing that we use in the proofs. Okay? And the question that we want to ask is, can depth Q decision trees distinguish the original distribution, the uniform distribution, from the conditioned high entropy distribution? Okay? And the answer is, well, and I should probably say that for concreteness, and this is the setup that we're interested in, the amount of advice bits and the number of queries will be polylogarithmic in the length in the number of random bits. Okay? Now, unfortunately, advice is helpful, right? I mean, it's immediate to see that if this suspicious guy is going to tell the adversary what is the value of the first bit, suppose the value of the first bit is 1, then conditioned on this, the value of the first bit is fixed, and it's obvious that by querying the first bit, the adversary can distinguish, okay? So even depth 1 decision trees that are non-adaptive can distinguish between these two distributions. There are more subtle examples showing that there could be like more subtle correlations that I'm not going to go into because I don't have enough time. But right, I mean, like, so there are other phenomena that can happen. So what do? So we prove these two results, which may be of independent interest. They're not complicated. The first one we call the forbidden set lemma, and it says something like that. Under the conditions of a setup, right, there exists a small set of indices, B. We call that the forbidden set. Here, small is polylogarithmic. And this has the property that decision trees that don't make queries inside the forbidden set cannot distinguish the original uniform distribution from the conditioned high entropy distribution. So that's the first lemma. For concreteness, right, in the case that I just showed you, if we were to forbid the decision tree from reading the first bit, it cannot distinguish. Okay? The second lemma that we prove is something that we call the fixed set lemma. So it's something with a similar spirit, but slightly different. So once again, under the conditions of a setup, there exists a small set of indices, B. Again, small is polylogarithmic, and a fixing V to the bits at that set, such that if we now consider two conditioned distribution, we considered the original random distribution conditioned on the bits in B fixed to this value V, and we consider the high entropy distribution with a further condition that the bits at B are equal to V, but now small depth decision trees cannot distinguish, right? So these are the two lemmas that we prove. So a few comments are in order. One is that the forbidden set lemma can be seen as a generalization of a very famous folklore lemma, which in this language is the case that Q equals 1. And this lemma is used all over the place, in many places. And so we think that this generalization may be helpful. Another comment is that in the previous paper with Viola, we had a forbidden set lemma, but only for non-adaptive trees. And this is one of the reasons why we weren't able to handle adaptive reduction. Another comment that I want to make is that since we published the paper, we found out that lemmas that are similar in spirit to the fixed set lemma are known in the cryptography community. The setup is slightly different and the conditions are slightly different, but it's the same kind of thing in work by Unruh, Dodis, Guo, and Katz, and Coretti, Dodis, Guo, and Steinberger. Okay? And finally, let me say that initially in the proof, we were used to using a forbidden set lemma, because this is what we did in the earlier paper, right? And so we had a proof based on the new forbidden set lemma, but the version that you have now is one where we don't use the forbidden set lemma, we only use the fixed set lemma, and it turns out that it's simpler to use the fixed set lemma in our application, but somehow I believe that the forbidden set lemma is more natural, right? It's something that may find more applications. Okay, so let me conclude. So we show that the XOR lemma for constant depth circuits cannot be proven by general black box reduction. So that's the main message that I want to take out of this talk. But let me be more provocative, right? We can ask a different question. Is the XOR lemma true for constant depth circuits? Right? Right? Maybe, right? I mean, the reason that black box reductions can't prove it is because it's not true. Here is a concrete question for experts out there, right? I mean, we have a technique, right, right, to rule out something like that. So, right? I mean, if you just come out with an example of a function where a constant depth XOR lemma doesn't hold, and something like that may be feasible, that will show, right, will give us even a better excuse than impossibility of black box reductions. Another interesting question is that you can ask is, what about non-black box techniques, right? So first of all, I should mention that, right, I mean, like, these are low circuit classes, so there are a lot of techniques that you can think about as non-black box, but I'm only thinking about hardness amplification. And in the context of hardness amplification, there is an attempt at a non-black box technique. There's a paper I had with Gutfreund and Tashma, which proves a very, very, very weak variant of amplification, but the point is that the proof that is given here there beats black box lower bounds and can bypass this kind of limitation. So that maybe this can direct us where to look for other proofs. Do I have more time? No. So since I don't have more time, I have 10 more minutes. So since I don't have more time, let me just say that there's lots of other stuff in the paper if you're interested in this kind of things, and thank you. Two more talks to go.
Yeah. Questions? Ronen? So have you looked into if there are crypto applications of these? I mean, how does it compare?
So, I mean, this is a different setup, right? Usually the kind of thing that you start from is a function that the adversary, right, like in crypto, you usually want to have a function where I can compute and even I cannot invert, right? So here we're talking about like only hard functions. So there are some applications in crypto of these kind of things, but not that many. So, right, it's far from the place where this is the barrier for crypto.
Right. Any further questions? If not, let's thank them again.